Welcome back to the next video, everybody. Today, we're going to talk about two different things. First of all, we're going to look a little bit more into the reduction map on the coefficients of cusp forms. And second of all, we're going to start looking at when certain Galois representations might satisfy Serre's conjecture. Okay, so recall from last video that Serre originally defined a cuspidal modular form over Fp bar of type nk epsilon with n and p coprime and k at least 2 to be any element of the image of the reduction map from the space snk epsilon tilde over zp bar to snk epsilon fp bar, where zp bar is the integral closure of zp and qp bar, and epsilon tilde was the Teichmuller lift of the character epsilon. Okay, and recall that Serre even acknowledged this definition wasn't going to work for his conjecture, ultimately because this map isn't always surjective. Okay, so that begs the question, when is this map surjective? Well, first of all, I'll give you a result that ignores the character. So lemma 1, let p be prime and let n be a natural number with n and p coprime. Three things are true. First of all, suppose k is at least 2. Then the reduction map from snk zp bar to snk fp bar is surjective if n isn't 1 or p is at least 3. So most of the time, if we ignore the character, we have a surjective map. Okay, what if n is 1 and p is or isn't 3? Well, the reduction map S1k Z2 bar to S1k F2 bar is not surjective if and only if k is at least 12 and either k is 1 mod 12 or 2 mod 12. Okay, so even there, we're sort of mostly surjective. How about when n is 1 and p is 3? Well, the reduction map S1k Z bar sub 3 to S1k F bar sub 3 is not surjective if and only if we get a similar condition, k is at least 12 and k is 2 mod 12. So even it's more restricted. Okay. So for a proof of this, you can see Cornell, Silverman, Stevens, page 216 in chapter 7, and then Deline has a write-up of this as well. Okay. How about if we bring back the character? So Carriol has a lemma about this that we will use. Okay, so Carriol's lemma, let n be at least 1. Let p be a prime not dividing n, and let k be at least 2. Let epsilon from z mod nz cross to zp bar cross be a character such that epsilon of -1 is -1 to the k. So this is a typical property that characters attached to cusp forms have. So that's why this is here. And let's let epsilon bar from z mod nz cross to fp bar star be its reduction. Let's consider the reduction map phi from snk epsilon zp bar to snk epsilon bar fp bar. So the same reduction as above, but now we brought the characters back into consideration. If p is at least 5, phi is surjective, period. We're in good shape. Serre's old definition and new definition kind of both work in that case. Okay, if p is 3, respectively p is 2, and f is an snk epsilon bar fp bar, and it's an eigenform such that rho f, the Galois representation attached to f, is irreducible, and f is not in the image of phi. So we're looking at things not in the image here. Okay. Then rho sub f is induced from q adjoin root -3, respectively q adjoin root -1. What I mean by that is the Galois representation rho sub f is just the induced representation from the subgroup G of Q adjoin root -3 up to GQ for some of pi, where pi is some representation of the Galois group G sub Q adjoin root -3, respectively G sub Q adjoin root -1. Okay, so we defined induced representations before in a previous video. One thing I want to say about this before we even get to use it, which will take place in later videos, is you might remember seeing Q adjoin root -3 before in my chapter 2 overview of Wiles and Taylor's proof of semi-stable modularity. Well, Carriol's lemma is sort of one of the originating reasons why this Galois group shows up there. Remember, we assumed we put 4 conditions on a residual Galois representation before we looked at how modularity lifted on it. And one of the conditions we put on it was that when you restrict it to this Galois group, it's absolutely irreducible. Okay, so that's going to come into play in this chapter. We're going to see where it comes from. One of the places it comes from is this lemma. Okay, so for a proof of this, you can see Diamond, the refined conjecture of Serre, which I'll call DRC from here on out. Section 2, this is in Coates-Yau elliptic curves, modular forms, and Fermat's last theorem, which I'll call CY from here on out. If you want Carriol's original proof, here's Carriol's paper, section 4.4. Okay, now on to the next topic. When does rho satisfy Serre's conjecture? So here is I would say this is the main theorem of the chapter. And what we're going to be doing is taking a look at the special cases of this that we can prove and that we need for modularity and Fermat's last theorem. So theorem 2, let's let P be a prime that's at least 2. Let's let rho from GQ to GL2 of FP bar be a continuous, irreducible, odd representation, which is modular of some type. Okay? Then rho satisfies Serre conjecture. Okay? So if you're modular of some type, then you're modular of the type that Serre's conjecture predicts. Okay. Now, before I get into the rest of this theorem, I just want to say Serre's conjecture is now a theorem as of 2008, Carre, Vinton, Berger. And Serre also showed that his conjecture implied modularity, hence Fermat's last theorem. Okay, so there is another proof of Fermat's last theorem out there if you believe Serre's conjecture as a theorem. So we're not going to take Serre's conjecture as a theorem because it was proven much later. It's also very hard. Okay, so this is the theorem we're going to work with instead, and we're only going to work with special cases of it. Okay, so if you're modular of some type, you satisfy Serre's conjecture. If you're continuous, irreducible, and odd, and P is at least 2, or P is at least 3, excuse me. Okay, moreover, if rho is FP bar modular of some type, let's say NK epsilon with N and P coprime, what's the relationship between NK epsilon and the NK and epsilon from Serre's conjecture? Well, N rho, the N from Serre's conjecture, will divide N. K rho, the K from Serre's conjecture, will be less than or equal to K. And epsilon will be obtained from epsilon of rho, the epsilon from Serre's conjecture, by composition with the natural map from Z mod NZ to Z mod N of rho Z. This whole thing was known well before Serre's conjecture was proven, okay? We just need special cases of this, but I will still send you, I'll give you references for a full proof. First of all, just see the Diamond article just mentioned about, it's talked about there. I think he just kind of covers the key steps, but he gives references. You can also see Ribbit report on Madel representations of the absolute Galois group of Q, which I'll call RRM from here on out, for an overview of the strategy. Also, there's references there. Okay, so starting next video, we'll start looking at which parts of the above results, in particular theorem 2, we'll actually need for modularity and for the proof of Fermat's last theorem. So I'll see you tomorrow. I won't see you Thursday. I'll take a day off for Thanksgiving. I'll put something up Friday, though, which I don't usually do. So thanks for watching, and I'll see you then.